Okay. All right. So last week, few of the students told me that they want more space in the PowerPoint so they can take notes. So um, I left some blank spaces for all the sample exercises, and the updated PDF file is on Web Campus. If you guys want, you can quickly visit Web Campus and download that if you want to take notes. Um, if not, that's fine. And a lot of the students have requested for the PDF file with my notes on it. So, and I didn't wanted to share last week because I had a very messy writing, but today I'll try to take take the note as neat as possible so I can share with you guys at the end of the um, lecture. However, I highly recommend you guys to take your own notes because some of my writing might not be enough for you to fully understand the material. Okay, so I will share the PDF file with my notes on it, but I highly recommend you guys taking your own notes as well. And for the homework, as for the homework, so um, it looks like there's a little delay to integrate grades in the Achieve to Canvas web canvas. So if there's a slight delay, please give them some time. And they told the Achieve Macmillan representative told me that we should check on our grades after the due date. So until the due date, the grades will continuously be updated. So just keep an eye on your grades, and if there's still discrepancy after the due date, then you can let me know and we can contact the Achieve Macmillan. Yeah, but the important thing is that you can visit your homework multiple times until the due date. But if you attempt to try to do your homework, excuse me, if you attempt to try to do your homework after the due date, then that might affect your grade and you can possibly receive point of zero. So whatever you've done earlier can um, go in vain. So please finish your homework before the due date. After the do not attempt to try to fix your homework or do your homework. Okay. I only have 65 students so far, so I'm going to wait about 3 more minutes and then I'll start the lecture. Okay.
Professor, I have a question.
Yeah.
So when you said that you recommend that we take our own notes, do you recommend that we take our own notes like based on your notes that you lecture on, or from the book, or from PowerPoints?
You should take your own note as I do the lecture.
Okay, you think that would be
Yeah.
best for just like retaining the information and learning all the concepts?
Yeah.
Okay, thank you.
Mhm. All right, can you guys see the screen that I'm sharing?
Yes.
Okay. Birdos, are you here?
Yes.
Okay, did you hold your first SI session?
Yeah, I held it yesterday.
Okay. Did many students join the meeting?
I think about 9 did, so that's a
No.
pretty good amount for SI.
Oh, okay. All right. So let's see how many of you guys are here. We have 69. Oops. So I have about 98 students, but I only have 70 so far. Anyway, going to go ahead and start the lecture. Okay, so continuing from the last lecture, to clarify what the exponents in the rate law represents, the exponents basically indicates how the rate is affected by each reactant's concentration. Okay, so because the rate at which NH4 reacts with NO2 depends on NH4 concentration raised to the first power, the rate of the entire reaction will double when this concentration doubles. The reaction rate is going to triple when this concentration triples. The reaction rate will quadruple when concentration of NH4 quadruples, and so forth. Likewise, because the rate at which NO2 reacts with NH4 depends on NO2 concentration raised to the first power, the rate of the reaction will also doubles when this concentration doubles. It will triple when this concentration triples. It will quadruple when this concentration quadruples, and so forth. Okay, but important note is that this order of reaction is determined experimentally. Okay, it should not be deduced from the balance equation. And these are some of the experimentally determined rate laws, and the coefficients in the balance equation, like 2, this has 1, 1, 1, 1. These coefficients in the equation it can appear to be same as the exponents in the balance equation, but that is not always the case. These rate laws is determined these are the experimentally determined rate law equation. Okay, so some of you guys might think because this reaction, the reactant has coefficient of 2, the rate might be something like this. This is totally wrong. Okay, so let's take a look at this example, the sample exercise where the rate law is already provided. So this is a rate law they provided, and again, these are determined experimentally. The example is showing that reactant A react with reactant B and then form product C. So if we plug in the concentration A and B into the rate law, and then we can obtain the reaction rates for each boxes. Okay, and since K is a constant and it will be same for the all three reactions, this value is insignificant in determining how fast and slow the rate for reaction 1, reaction 2, for box 1, box 2, box 3 reactions. Okay, so this question is asking you, so it says that each of the following boxes represents a reaction mixture in which A is shown as red spheres. This is A, and then purple is sphere B is purple, and we need to rank these mixtures in the order of increasing rate of reaction. So we need to find rate of reaction for box 1, 2, and 3. Okay, so concentration is basically how much we have, and since box 1 has 1, 2, 3, 4, 5 red spheres and 1, 2, 3, 4, 5 red spheres, we can plug these values into a rate law equation. So we have rate law equation of K, constant K, concentration of A times concentration of B to the second power. We plug in concentration A, we have 5 spheres. And we have also 5 spheres for B. Then we have 125, and rate constant K is still there because we don't know what the rate constant is for this problem. Same for box B, we're going to plug in the concentration of A here, concentration of B here. We have 1, 2, 3, 4, 5, 6, 7 sphere, red sphere. So we have 7 spheres for A. So we are going to plug in 7 for A. We have 1, 2, 3 for B. So we're going to plug in 3 for B. If you do the math, we have 63, and K rate constant is still there. Box 3, same thing. We only have 1, 2, 3 sphere, red sphere. So we're going to put 3 for A, and we have 1, 2, 3, 4, 5, 6, 7 for B. So we're going to plug in 7 for B. And then if we do the math, we have 147, K rate constant K is still there. So because rate constant K is a constant and it will be same for all three reactions, okay, this value is insignificant in determining how fast and slow the rate is. It's not going to affect the entire rate. Okay, so just by comparing the number in the front, we can rank the rate of the reaction. So the slowest will be box B, and then followed by box 1, and then the box with fastest reaction rate will be box 3. This is the answer. Okay. Let's take a look at another sample exercise. For this exercise, the concentration of two reactants and the initial reaction rate are given, and we need to determine the rate law, and we need to determine the rate constant. And for question C, if we know the rate law and rate constant, we can easily find out the rate of the reaction for a totally new experiment where concentration A is 0.05 mole and concentration of B is 0.1 mole. Okay? So yeah, so from the future, what I'm going to do is I'm going to leave these massive blank spaces for you guys to take notes for all these sample exercises. So this version of PDF file is already uploaded on Web Campus, so you can download this. Or after this class, I'm going to upload the file, PDF file with my notes on. You can download that as well. But if you don't want my handwriting, if you want to write your own with your own handwriting, this blank version is also available on Web Campus right now. So for question A, we need to determine the rate law. And rate law has equation of constant K, concentration of A to the power of M, concentration of B to the power of N. We need to find M and N, okay, in order to find the rate law, okay? So what we can do is we can use experiment 1 and 2 where concentration A is held constant. As you can see, concentration A is held constant and concentration B is varied, okay? So utilizing these two experiments, we can deduce the order of rate law respect to B, okay? So let's if you divide rate of experiment 1 by rate of experiment 2, that will equal to constant K of concentration A of experiment 1. This 1 indicates experiment number, okay? Concentration B of experiment number 1. Divided by rate of 2 is equal to constant K concentration of A for experiment 2, concentration B of experiment 2. Okay, so as you can see, because concentration of A is held constant, we know for sure that they are same, so we can cancel that out. The constant K is same for both reactions, so we can also cancel that out. So what we have left is concentration of B for experiment 1 and concentration of B for experiment 2. Okay, and
I have a question.
rate, yeah.
So essentially what you would want to do to find the rate of law is just to divide the concentrations by each other of A and B, and then since A cancels out, then you're left with just B1 over B2, and that would be your answer?
What's your question again?
Since okay, because right now you're dividing the concentration or the constant, sorry, of A and B, like A1, A2, B1, B2. So then since those cancel out, you're just left with B1 and B2, and that would you would just divide those two, and that would be your answer.
I'm not done with the math, so bear with me for a little while.
Okay.
You will understand in a little bit. Okay, so did you understand up to here where we get concentration of B from experiment 1 divided by concentration of B experiment 2?
Yes.
How we You got this part? Okay. So then the rate 1 is this value. Rate 2 is this value. What can you tell? Are they same or different? They're same. Okay. So this rate 1 divided by rate 2 is basically going to be 1 because they're same. Okay. And then you're going to be you're going to plug in the concentration of B for experiment 1 and concentration of B for experiment 2. Concentration of B for experiment 1 was 0.100. This value, you will have power n. Concentration of B from experiment 2, you have 0.200 to the power of n. Okay, this basically is 1 over 2 to the power of n. Okay, so you have you have 1 equals 1 over 2 power of n. If you solve for n, you will know the exponents for concentration B. Okay, so how to solve this? Use algebra. Natural log of 1 equals 2 n natural log of 1 over 2. You solve for n. Natural log of 1 divided by natural log of 1 over 2. Natural log of 1 is 0, right? 0 divided by anything will be 0, so n is 0. So from this, we were able to find out that the exponents for concentration B is going to, this n is going to be 0. That tells us that rate law is 0 order in B. That means rate law is independent of B. Does this make sense? When the power is 0, the rate law is 0 order in B, and the rate law is independent of B. We're not done for part A. We need to find n. We need to find, so we're already done with n, which is equal to 0, and we're going to find n. So for n, we're going to use experiment 1 and experiment 3. Okay, for experiment 1 and experiment 3, we know that concentration B is held constant, 0.1, 0.1, but concentration of A is varied, 0.1 for experiment 1 and 0.2 for experiment 3. Okay, so we set up the same same equation as we did for up there. So if you have rate 1 divided by rate 3, or because experiment 3 has larger value, we can also do rate 3 divided by rate 2. That will allow us easier math. Rate 3 equals to constant K, concentration of A from experiment 3, concentration of B from experiment 3, divided by constant K, concentration of A experiment 1, and then concentration of B from experiment 1. Is everybody okay so far? Okay, then we know that concentration B is held constant. They're same, so we're going to cancel them out. Constant K is always same for all the reactions, so we're going to cancel this out also. So what we're left with is rate 3 divided by rate 1 equals to concentration A experiment 3 divided by concentration A experiment 1. Okay, so we're going to rewrite that. Rate 3 is, according to this table, 16.0 times 10 to the negative 5 divided by 4.0 times 10 to the negative 5 equals to concentration A for experiment 3 is 0.2 power of m. Concentration A for experiment 1 is 0.1. Okay, and this will be 4 equals to 0.2 divided by 0.1 is 2 to the m. So again, you solve for m using algebraic equation. Natural log of 4 equals to m natural log of 2. Solve for m, you have natural log of 4 divided by natural log of 2, you have 2. Okay, so from these two part 1 and part 2, what you found is that the rate law for this experiment. You found m to be 2, so you put 2 here. You found n to be 0 up here, so you put 0. So basically, the rate law is concentration A squared. Okay, so this rate law is independent of B. Concentration of B does not matter in affecting the rate law of this experiment. Okay, any questions so far? All right. Yep.
I was gonna say, so rate law is basically finding the equation, and we didn't know the exponent, so that's what we needed to figure out.
Exactly. Yeah. So we were provided concentrations, and we were provided the initial rate, but we do not know the rate law. Okay. So the question was asking us to find the rate law. So what's important in the rate law is the exponents of these concentrations, right? So we were doing all these math to find the exponents for the concentrations. Is that clear? Okay, moving on to part B, we need to find the rate constant. Okay. So we know that rate law is now constant K times concentration A square. So then we can solve for K. It's going to be rate law, rate of any equation divided by concentration of A squared. So we can pick any experiment that is provided over here. You can pick experiment 1, you can pick experiment 2, you can pick experiment 3, and then you can figure out the constant K. Okay, so I'm going to pick experiment 1. Okay, so for experiment 1, we have initial rate of 4.0 to the 10 to the negative 5, and concentration A is going to be 0.1. I'm going to plug that information here. So I have 4.0 times 10 to the negative 5 mole per second divided by concentration A, 0.100 mole square. Okay, so if you do the math, you're going to have 4.0 times 10 to the negative 3, okay? And then, important part, a lot of people make mistakes for this part. So as you can see over here, the unit in the numerator, we have mole per second. And then denominator, we have mole squared. And a lot of people forget to square the unit as well. So if we have mole square, what we're left with is mole to the -1 and second to the -1. Okay, and that's going to be unit for this. If you did not square this m, the m will cancel out and you're going to be left with second only, right? Second to the -1, power of -1. This unit is going to be incorrect. Okay, so make sure you double check your unit before you submit your answer. Okay, and even if you made a mistake in the math part, you can just check the rate for the unit for constant K will be mole to the power of -1 and second multiplied by second to the power of -1. So for C, you are asked to find a rate for a totally new experiment. Okay, so you are performing experiment 4, and the new concentration they provided was 0.05 mole and 0.1 mole. You need to find the rate. Okay, so then what you're going to do is I'm going to write the information that is already provided. So the rate law is K to the power of 2. So then the rate is going to be, we already found constant K from B. We just want to plug in this information here. 4.0 times 10 to the -3. And then multiply by concentration A, which is 0.05. Okay, and then this will allow us to have if you square the 0.050, you have 0.0025 mole square. If you do the math, you're going to have 0.01 times 10 to the -3. And now as for the unit, you have mole multiplied by mole square. This basically means you have this. Okay, so this mole and this mole cancels. You're going to be left with mole. So your unit is mole per second. Okay, so your final answer is going to be mole per second. As for the scientific notation, you don't want to have anything below 1. Okay, it should be between, the number should be between 1 to 10 for scientific notation. So we're going to rearrange this. Okay, so go back to, you're going to be, the final answer is going to be 1 10 to the -5 more per second, and this is going to be your final answer. Okay, so that's it for A, B, and C. Any questions so far? So again, all of these, I try to take a nicer note today, so I can upload this at the end of the class. So yeah, take a look at the math and let me know if you have any questions. Okay, moving on to relative value of K. So what does the rate constant K represent? Okay, the rate constant K that we just found from this experiment. What does it tell us? The relative value of K indicates how fast the reaction is. Okay, so for a reaction that has K value of 10 to the power of 9 or higher, the reaction is considered fast. If the rate constant is below that, the reaction is considered slightly slower. Okay, so that's basically what the rate constant tells us. Okay. So from here, we will take a deeper look at the reactions with various different orders. So we're going to deeply examine the first order reaction, second order reaction, and zero order reaction. Okay, so first of all, let's take a look at the first order reaction. The first order reaction is one whose rate depends on the concentration of single reactant raised to the first power. Okay, so if you have a equation where reactant A produces product B, okay, when a single reactant is involved in the reaction, then you're going to write the rate law as rate equals to constant K multiplied by concentration A. So the example of first order reaction is going to be the reaction where methyl isonitrile is transformed into acetonitrile. So in this reaction, a single reactant is solely responsible for generating a product. Okay. And then, so in the previous section, we haven't really examined examples where time t affects the rate law. So far we were able to calculate the rate of reaction from the rate constant K and the reactant concentration. But when time involves, the reaction gets way more complicated. And in this following section, we're going to examine examples where time involves, okay? And we will see how the rate law is related to the concentration of reactants and products versus time. So the math involves some calculus operations, and I'll show you, but you don't have to memorize the entire process. What you have to memorize is going to be these final equations. So I'm going to show you the entire math, how we arrived this final rate law equation for the first order reaction when time involves. You do not have to remember or memorize the entire process, but you do have to memorize this final equation. Okay. So I'm going to show you the math. So this is a basic equation that you are familiar with. Okay. So for first order reaction, you only have reactant A matters. So the rate of the reaction is going to be constant K multiplied by concentration A. And this rate equation tells you that the change in concentration of A over change in time determines the rate. So basically they're the same. So if you set these two to be equal, you have this. Okay, so if you rearrange this, you're going to have K concentrate. If you divide both sides by concentration A, you're going to have negative delta and then when concentration A cancels out, you're going to be left with something like this. And then when you rearrange this, you have something like this. Okay, so this is this. I think textbook only shows you how you get here from here. It doesn't show you the process. So this is going to be the entire process. Again, you don't have to memorize or memorize this. Just take a note how I came up with this from this. Okay. So from here, what we need to do is we need to use the derivatization. Okay, so derivatives in calculus is used to find the rate of change of a quantity with respect to the other quantity. We need to we're examining the change in concentration A with respect to change in change in time. Okay, so we're going to derivatize these two where it has delta. Okay, so this will become so I'm basically derivatizing this. Okay, derivatizing the concentration A, derivatizing time t. Okay, so we will integrate. So this will become I'm not sure how many of you guys are familiar with the calculus, but this is the calculus is utilized to derive the final equation, so I have to show to you guys. So we solve for the differential equation and we integrate from the initial concentration to the concentration of A at some time t. Okay, and same for the time. We are going to integrate from the initial time t equals 0 to the sometime t. Okay, and this will become we're going to evaluate the natural log of A concentration of A, initial concentration of A to the concentration of A at some time t, and then okay, and we are going to rearrange this. Okay, and use a fundamental theorem of calculus. The left side is going to be this, and then the right side is going to be this. Okay, and if we rearrange this, we're going to arrive and this equation is the equation over here, what you have to memorize. Okay, so again, you don't have to go over this calculation. I just have to show you because I just want to make everything clear, but just know that the only thing you have to know is that we derived first order fourth order reaction equation using these two equations combined together and using the integrated rate law to arrive the final equation. So this equation for the first order reaction has a form of y equals mx plus b. So your y is going to be natural log of a at some time t, and then your m is negative k, and then x is time, plus your b is natural log of initial concentration. Okay, so what does this tell you is that when you graph this equation, your y-axis is going to be natural log of concentration A time t, and then your x-axis is going to be time t. Okay, so the plot of natural log of A versus time t is going to be linear. Okay. All right, so let's take a look at this example. Because a single reactant is reacting to form product, this is the first order reaction. Okay, and if you plot the natural log of initial concentration, okay, you're going to have a straight line, and that's what we're seeing here right now. If you just plot the concentration itself, you will see a curved line. This is not straight. Okay, but if you have a natural log of concentration, you're going to have a straight line when you have natural log of concentration versus time. Okay, so always, first order reaction, when you plot natural log of concentration versus time, you are going to have a linear line. And this is going to be an important evidence to tell you whether, to confirm that this reaction is first order or not. Somebody had a question?
Yeah, I have a question. So
Yeah.
did you say that if it's one product, it means that it's one order? I mean, first order?
No, one reactant.
One reactant is one first order.
Yeah.
Okay, thank you.
One reactant producing one product is first order. Okay, and then we're going to see some examples for second order, and you will have a much better idea. Okay.
And these equations are to find the rate laws of like first order and second order. Like if there's only one reaction?
This is just first order.
Yeah.
Yeah. This is
Okay.
just first order. We haven't gone over the second order yet. We're going to go over that soon.
Perfect. Thank you.
Uh-huh. All right. So again, if we were so when we know that the reaction is first order, and we can utilize the first order reaction equation to find the rate constant K. Okay.
Dr. Lee,
Yeah.
what does the subscript T and the subscript 0 mean again?
Okay. So 0 means initial concentration A. So
Okay.
concentration A in the beginning. Okay. And then T represents concentration A at T represents concentration of A at some time T. Okay. So later concentration. So concentration A0 is initial concentration. Concentration A at T is sometime later. Concentration of A at sometime later. Does that make sense?
Perfect sense. Thank you.
Yeah. Okay. All right. So when we know that the reaction is first order, we can utilize the first order reaction equation to find the rate constant K. Okay. So as we know, the y is going to be natural log of concentration A at time sometime t, and then for this equation, from this equation, we can know that the slope of this linear line is negative k. Okay, so and then the y-intercept b is going to be natural log of a0. Okay, so the reason why I'm showing this is that if you were provided first order reaction and if you're provided some other values, you should be able to come up with the come up with the rate constant, which is a slope, or you have to be able to come up with the y-intercept, which is natural log of initial concentration A. Okay. So we're going to move on to, let's take a look at a half-life reaction. So half-life basically means the amount of time required for the concentration of initial reactant to reach half of its initial value. Okay, so we will utilize the first order reaction and substitute the concentration A by the initial concentration divided by 2. So this is the first order equation that we derived earlier. Okay, and then because half-life concentration is basically initial concentration divided by 2. Okay, we're going to plug in this in here. Okay, and that's what we have over here. Okay, so natural log of half of the initial reactant concentration equals to negative K time to reach half of the concentration plus natural log of initial concentration A. Okay, so we rearrange this math, we come up with this, and then here, and you will arrive. This is just basic algebra. I don't have enough time, so I'm not going to go over the detail. Okay, if you have time, you can play around. It's very, very simple. What you're going to arrive is this. Okay, and this is what you have to memorize. So the first order reaction, okay, you have to, first order reaction equation is what you have, the first thing you have to memorize, and then this is going to be the half-life of the first order reaction, and you need to memorize this equation as well. This equation tells us time required to reach half-life. Okay, half-life, or half-life means half of the initial concentration. Okay, and the relationship is the time to reach half of the initial concentration is 0.693 divided by constant K. Okay, so that's that for first order reaction. Moving on to second order reactions. Second order reaction is one for which the rate depends either on a single reactant concentration rate raised to the second power, or concentration of two different reactants, each raised to the first power. So, for example, if you have product A going to, if you have reactant A producing product B, let's see, product. But if after the experiment you figure out that this reaction cannot be explained by first order reaction, from the experiment you found out that you actually need twice as, you need to double the concentration A in order to reach the reaction rate, then you need to arrive to this equation. Okay, and again, this rate law is determined experimentally. Okay, so someone previously asked me if it's always first order when you have one reactant. Yes and no. Okay, so you need the experimental, from experiment, you will come up with the appropriate rate law, and sometimes a single reactant can obey the first order reaction, but sometimes it can also obey second order reaction as well. Okay, so if the reaction requires something like this, the rate is now second order. Okay, so that's the first example. And let's say if you have two different types of reactants producing product B, product, okay, then the rate is going to be constant K times concentration A, concentration B. The exponent for A is 1, exponent for B is 1, so the total order is going to be 2. So the order is going to be dependent on the exponents, right? Okay. So for this, it's second order reaction, and this is also considered second order reaction. Okay, so let me summarize whatever I said, and then I'm going to write here. So the second order reaction is one for which either single reactant concentration raised to the second power, or concentration of two different reactants, each raised to the power. Okay, if the sum of the exponent is 2, the total reaction is considered second order. Okay, so let's come so remember we did crazy math to arrive first order reaction.
Can I go back, please, to see what you just wrote? I'm sorry. I'll take a picture of
okay,
it.
yeah.
Thank you.
Yeah. This will be available on Web Campus after the class, by the way. Okay.
Okay, thank you.
Yeah. Okay. So just as how we did the crazy math calculation to achieve first order reaction, we can do the same thing for the second order reaction. Okay, so for now, for this second order reaction, the rate is now going to be K times concentration A power of 2, okay, instead of 1, as we observed in first order reaction. Okay, and again, we also have this expression where concentration of A, change of concentration A over change of concentration, change of time. Okay, if we set these two equal to each other, we arrive this. Okay, and then we rearrange this to here. Okay, and then we were going to also do the derivatization for these delta. Okay, so you do the d okay. If you do all the mathematical the calculus derivatization, you're going to finally achieve these and this equation. And I'm not going to show you all the calculation because I'm running out of time. What you have to memorize is this equation over here. This is the second order reaction equation. Okay, so let's compare the first order and second order reaction. This is the first order. This is the second order. Okay. First order also has y equals mx plus b form. The first order also has y equals mx plus b form. Second order also has y equals mx plus b form. However, their y are different. Okay, the linear relationships for first order and second order are different. Okay, so for first order reaction, when you plot natural log of concentration A versus T, you are going to get linear line. For second order reaction, when you plot 1 over concentration A versus time, you're going to get a linear line. So for both reactions, you can obtain linear line, but then your y-axis expression is a little different. And we're going to see the specific example over here. So this is an equation where rate equals to K times concentration of NO2 to the power of 2. So it's a second order reaction. If you see over here, if you do natural log of concentration of NO2, you only get a curved line. Okay? But if you plot 1 over concentration of NO2, you get a straight line. Okay? So this straight line indicates that this the relationship between NO2 to the entire rate is second order. Okay. So although you have a single reactant, you should not express this as this is totally incorrect. Okay. Although you have single reactant, you're going to express the rate loss as follow. Because we already proved that this graph showed that the reaction is second order in NO2. So
Dr. Lee,
yeah.
how did that go? That last, I didn't. How was that second order again?
Oh, okay. I'm going to summarize one more thing. So when natural log of A versus time is linear, the reaction, the rate is first order. When 1 over A, concentration A, versus time is linear, then the rate is second order. Okay, so these are the differences. Okay, and as you can see over here, which one gave you a straight line? Graph of natural log concentration of NO2 versus time, or 1 over concentration of NO2 versus time? Which one gave you a straight line? This gave you a straight line, correct? Okay, that's why we say the rate is second order, because 1 over concentration A versus time gave you a linear line. Did that explain?
Dr. Lee?
Yeah.
I have a question too. So when you're referring to a second order reaction,
Mm-hmm.
is that referring to half of the time that the reaction takes place? Or could you like explain that further, like more detail?
Oh, okay. So, mm, so I think you're confused. So half-life is basically the amount of time takes for the starting material to become half of the initial amount. Okay, so you can so here we observed half-life of half-life for first order reaction. Okay, so this is a half-life for first order reaction. That is totally different from second order reaction. Okay, we are going to go over the half-life of second order reaction. Okay, so for half-life, T is always going to be 1.5. Okay, but this general equation over here is a general equation for second order reaction. This is not for the half-life of second order reaction. Half-life equation for second order reaction, we haven't explored yet. We need to explore it in a coming up section. Okay, so please do not get confused. This equation over here, this is not half-life for second order reaction. Okay,
Okay,
is that clear?
Yeah, so second order reaction, that is the linear reaction, correct?
Linear reaction, yes.
Okay, makes sense.
Okay.
Thank you.
And you can plug in any time. Okay, but now we're going to, previously we observed half-life for the first order reaction, right? Now, so what about the half-life for second order reaction? That's what we're going to explore right now. We can use the same substitution that we did for the first order reaction. Okay, so this is the second order reaction equation. Okay, this is the second order reaction equation that we derived just right now. And then we're going to substitute the concentration A as initial concentration A divided by 2. Okay, because after half-life, your initial concentration drops to half of the initial your concentration drops to half of the initial concentration. Okay, so after half-life, concentration A becomes initial concentration divided by 2. Does everyone agree with this? Okay. What we're going to do is we're basically going to substitute this into here. Okay, and then again another rearrangement, just basic algebra, and then we're going to derive this equation. Okay, so here is a very good comparison between half-life reaction for first order reaction versus half-life of second order reaction. So this is a half-life for first order reaction. Do you remember from this previous section? Okay, and this is going to be half-life of second order reaction. Okay, so they are different. Half-life for first order reaction, half-life versus half-life of second order reaction, they are totally different. Okay, one interesting thing to note is that while half-life of first order reaction did not depend on concentration, do you see any concentration A or B expressed here? No, right? T is just 0.693 number divided by constant K. But for second order half-life reaction, there is concentration involved. So half-life for second order reaction is concentration dependent. Okay. Again, the difference between half-life for first order reaction versus half-life for second order reaction is that half-life for second order reaction is concentration dependent. Okay. Sometimes, so we've already explored first order reaction, second order reaction, and now we're going to explore zero order reactions. Occasionally, the rate is independent of the concentration of the reactant. The rate is totally dependent on constant K, reaction constant K. Okay, these are called zero order reactions. So no matter what concentration of A or B you have in the beginning, it doesn't really matter. Okay, the rate is going to be dependent on reaction constant K. Okay, and these reactions are linear in concentration. So if you have concentration A versus time, that will give you a linear line. Okay, but if you plot concentration A versus time for first order reaction, you will never get a linear line. In order to get the linear line for first order reaction, you need to plot natural log of here, you need to plot natural log of concentration A versus time in order to get a linear line for first order reaction. Okay, so that's the difference between zero order reaction and first order reaction. So again, this is another equation that you need to memorize. Integrated rate law for zero order reaction is as follows. Okay. We're going to do a sample exercise. We have about 3 minutes, so we might not be able to finish this, but we'll see how far we can go. Okay, so let's read the question first. The decomposition of a certain insecticide in water at 12 degrees Celsius follows first order kinetics with the rate constant 1.45 e to the negative 1. Okay, a quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of this. Okay, assume that the temperature of lake is constant. You need to find what is the concentration of the insecticide on June 1st of the following year. So they're asking for the concentration of the insecticide after 1 year. So the time is time 1 year. Okay, so let's summarize, let's reorganize the given information. So the given information is constant K, 1.45 e to the negative 1. Okay, and then we're also given initial concentration, which is this, 5.0 times 10 to the negative 7 gram per centimeter cube. Okay, so the question A is asking what will be a concentration of A after 1 year. Okay, we're going to use, because they already indicated that this is first order reaction, we're going to use first order reaction equation, which is natural log of A at time t equals minus KT plus natural log of initial concentration of A. Okay, so we plug in all the information that we already have. We have K, which is 1.45 e to the negative 1. Time, we have 1 year, right? They're asking for concentration after 1 year. So the time they're asking is 1 year. Okay, plus natural log of the initial concentration is also provided. So we're going to plug in 5.0 times 10 to the negative 7 gram per centimeter cubed. Okay. Then we do the math. We have negative 1.45 plus this value will give you negative 14.51. Okay. Which equals to negative 15. Okay, so then natural log of concentration A after 1 year is going to be negative 15.96. Again, algebra, if you have natural log of x equals y, then x equals to e to the so you use the inverse natural logarithm. You use this to come up with concentration of A after 1 year. It's going to be e to the negative 15.96. You plug this value in calculator, you will get 1.2 times 10 to the negative 7. The unit is gram centimeter cube. Oh, by the way, over here, you have year to the negative 1, and you have year, so they cancel out, so you don't get any, the year is all canceled out, and you only have a gram per centimeter cube throughout the math and as for the final concentration. All right, so that's it for today. I'm going to hang around for another 5-10 minutes just in case anybody has questions.
Dr. Lee?
Yeah.
So pretty much what I gathered today was we learned about the rate laws, first and second order, and then the first order half-life rate law and how to apply them.
And then another thing, half-life for second order reaction, we learned that too, right? Yeah.
Oh, we learned second order reaction. Okay, and then also the second order reaction for half rate.
Yeah. So half-life and half-life. Yeah. Yeah. Okay. So
those 5 things, right? The rate law, the first order, second order rate law, and the first and second order half-life rate law.
Oh, and then we also learned the zero order, right?
Oh, that's right, zero order.
Yeah, zero order. Okay.
Okay.
Yeah.
Thank you.
Just a lot of calculation and math today, but yep, those are the basic 5 things that we learned today.
Thank you so much, Dr. Lee.
Okay.